So it's still here recording. Yes. Okay. So all right. So what I was saying is I would like to take as a way to always start as a habit is to start by asking questions about what happened during the previous week. So if you have any question regarding what we did last time, or even before that, no problems. If you have any questions, I would like you to start with that. So the questions, before we start, we just clear anything that is maybe remaining from what was not clearly understood from last class. So this is the first part, and then I'm just going to be talking about the second thing is about the mini test. So because this is the first time we're going to do that, and I had some questions about when this is going to be. I mentioned in the last week's video, actually the recording is there, I mentioned last week that the mini test is going to be either in the beginning of the class, like right now, or in the middle, or towards the end, or at the end. So it will depend on the week, and depend on the topics, if we need to take some break. So it's going to be changing, but the idea is that you have to be ready. And in order to, again, make even more opportunities for you to be ready, I actually added in Blackboard, as you may have seen, here this is mini test review. So these mini tests are going to be like the real ones that I'm going to add here in the assessments. The real ones are going to be here in the assessments. These ones are going to count. These ones are not going to count. So if you click on this mini test right now, for example, it will tell you that time test, this has 10 minutes. It will have, I think, 8 questions, 0.25 each. The test will save and submit, blah, 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 the same thing. Force completion, the test will finish after the timer is gone. The test will allow multiple attempts. That means you can try again the same test multiple times. You can do it again and again and again, as many times as you want, actually. That's a good idea to do that, because every time you got a random question that is going to show up. Now this here, it says you will be previewing the assessments. That means at the end you will see which one is correct, which one is not correct, and your result won't be recorded, which means these are not going to be in the grades, in my grade center. When you're going to see the grades, these are not going to be anywhere. So this is just for you, so you can practice for the test one. And this mini test one is going to be from these questions from here. So it's going to be the exact same pool of questions. So what I have a big number of questions saved somewhere, and then I select 8 out of those big number of questions. So every time you start the mini test, it's going to again randomly select 8 different questions. Okay, let's see. Some people were writing something. Okay, the microphone, and okay, all right. So yeah, everybody's hearing me. So any questions regarding this? And so we have this mini test. These are for you. Every week I'm just going to upload something. This is about the test 1, which is going to be, if I say mini test review 1, it's going to be exactly the same thing you're going to see for the actual mini test that we're going to be doing here. This is the one that is going to have 2%. So 8 questions out of 0.25 gives you 2 marks. So these are going to be the 2 marks. All right, let me check the questions. Is it at the beginning or at the end? Well, I just mentioned that earlier. Maybe you just joined. But I mentioned that this is going to be depending on the week. I don't know. It might be the beginning, the middle, the end. There's nothing that's going to be actually finalized. Just don't write these type of things, too long things. I'm not here to read. I cannot read a lot of things, okay? Just if you want to talk a lot, just talk to me directly using the microphone. It's going to be much actually easier for me to do that. And then actually to be able to read while I'm talking, while I'm presenting, is going to be much difficult, okay? So there's something that I don't know, I'm not going to read also the automatic. I don't have time to do that, because during the lecture I want to be just focusing on reading everything. So if you'd like to read something, a quick question like this, fine, I can answer that. But if you'd like to write a lot of things, that's not the time, all right? So that's great. This being said, let me now go back to here. Get back to here. So the idea is that for every week, for every one of these mini tests, you're going to be having some review that you can prepare on, like this thing here over here. And this review is going to be the exact same questions that are going to show up in that mini test. That means if you practice maybe all the questions, if you practice enough, you might have seen all the questions that are going to show up in this mini test, which is fine by me if you're able to understand all those questions in the pool of questions. And if one of them comes back to you in this assessment, then it's going to be the same questions. The only thing that is going to be different from the mini test review than from the assessment is that right now the mini test review is out of 10 minutes. That other one, that assessment, is going to be in less than 10 minutes. So that means I have not decided how long, maybe depending on the week, depending on the type of questions. Some questions require more time, some questions require less, but it's definitely going to be less than 10 minutes. So maybe, for example, 8 minutes, 7 minutes. That means you have 1 minute per question, or a little bit less than 1 minute per question, which is still enough. We're going to see, if you've seen the questions, you see that it takes less than a minute to less than maybe 10 seconds to answer the question. Of course, if you know, you have reviewed properly. So I hope this is clearing out this. Let's see if there's any last minute questions. When will be the real mini test? Well, I'm going to tell you during the class when this is going to happen. So this actually serves for two purposes. The first one is that I will use this mini test as a time to like take a break from you to get your attention back, because from last week, 2 hours, 30 minutes of talking and focusing, I might lose people. Some people might not pay attention, they might do something else. While now with this mini quiz, you don't know when this is going to happen, and this will force you to be with me in the class. Of course, now just be careful. If you need to go to the bathroom, you can go to the bathroom anytime you want. Just make sure that you don't spend too much time outside, just outside of the online class. All right, so yes, somebody wanted to lower. Yes, I see someone is raising their hand. Okay, go ahead, Ryan.
Yes, Doctor, good evening. I'm a student who visit you at morning today,
All right.
but I want to remember you about the announcement and the automatic attendance.
Yes, thank you very
Also,
much. Yes, for the
also, Doctor,
attendance. Yes.
my question is about the test. We will test only the quiz, or we will have the real test now.
No, right now you can do the test. Okay. Okay, that's a good point. Let me do one thing, because I sent the announcement kind of late. So I will do one thing. Right now I'll just give you maybe 10 minutes so you can practice the test, or maybe something like that. 10 minutes you can practice the test if you haven't seen that until now. I will give those 10 minutes right now for you to do. So okay, start. Go ahead and go with those 10 minutes. I'm just going to stop sharing my screen, and then go to this and test. Actually, if you already tried it, you see that's kind of convenient. Hopefully, inshallah, you will find that it's convenient, but also it's actually, as I mentioned, the same questions that you're going to have. The other thing I would like to talk about is the attendance, and thanks for reminding me that. I will just take a minute to actually show this OneDrive. I will share my screen again. I want to talk about the attendance and how this is going to be. So last week, the attendance, even though it was taken by the system, and I'm going to show you what I get when the system is actually working. When you log in, let me share my screen again. This is what I can get. I get some kind of report that shows me who is logged in and for how many times they logged in, and I'm going to show this to you so you can see. And the attendance, I did not enter this attendance from last week. This is the last week's class. As you can see, it gives me the this type of information: last join, last leave, and then it gives me how many times, what's the total amount of time that they spent online, how many times they joined and left, and I just added these two columns to make them calculate as some kind of formula to give me how many minutes. Then I can convert to how many periods they attended. So I can see like some people attended 3 periods, some people attended 4 periods because maybe they were online a little bit before and then they left way later. This is maybe not a good sign actually. Maybe they just opened it and then left. Allah alam, I don't know. You know, I cannot know exactly what's going on. I can just do what I think might be the conflict. I don't want to spend too much time checking is this one actually attended, did not attend. That's your thing. Now my only way to motivate you to attend that I'm going to focus on are those mini tests, because the mini tests, you don't know when they're going to show up. Now if you don't attend, well fine, 2 marks are gone. It's not a big deal. You have many more to come hopefully to get it back. But that's, so this here, I'm just going to take this. If you have 3, that means you attended. You have less than 3, that means you have only 1 period that you attended. The other 2 are going to be absent. So this is the thing I'm going to do. For example, you attended 2 periods, that means 1 period is going to be absent. So that's what I'm going to enter in the system. So I'm not going to just spend too much time on that, because you're actually a lot, and I'm not going to do an investigation on which doing what, because that's not my job. My job is to just convey the information, share my information, and my job, actually the main thing that I'm paid to do is to answer your questions, because I'm not showing you anything that is confidential, top secret, whatever. So everything is available online. I have many sources that can maybe better, most likely better than mine, and yeah. So, but my objective here is that I answer your questions. So this is how this attendance is going to be. If you have any questions or something about it, yes, please go ahead. Yes, Ryan? No? All right. So let's take this few minutes, go to this mini test here, and take the mini test review, check the questions, and you can see it begins. Oh, I forgot to say another thing. Yeah, for when I said the only difference between the mini test review and the actual mini test is going to be the timing, right? But another thing is going to be actually also, right now you can just move between questions, go to the first, go to the next, no problems. But the backtracking is not going to be available during these mini tests. So if you move to a question to another, it's done. You're not going to go back. Okay, and it's better to use this question completion status so you can actually follow in the mini test review. Honestly, I'm still not sure about this, but yeah, no, I'm not going to do the backtracking. Just the time is going to be different. That's enough, because sometimes maybe some people can click on this without paying attention. So okay, I'll make it even easier on you. No, the backtracking is going to be available. That means you can move between questions, no problems. You can just move between different questions, and then I'm just going to take the answers. Just if you see the equation, you can be able to see which one the answer. I'm just doing anything just to see some kind of result, whatever. And then if I skip something, I'm just going to skip it. And if I click on save, I mean, I can just maybe, you cannot submit until you go to the last one. I'm just going to go to the last one. I'm going to save and submit. It tells me not all have been answered. Question 6 and 8 are not answered. So in case you forget, but I would like to show you this. You click on OK, and this is what you're going to see. You see how much time it took you to answer, and then these questions, this one right, wrong, etc. It's going to give you like an indication of what you did. All right, so this being said, let's check the question again. Yes. Ryan, go ahead.
Doctor, one question of the review test. It is talk about the declarative sentence that is either true or false.
Okay,
I'm not sure about.
If you have something specific, right? I don't think it's going to be easy to share it now with everybody. Now, what I suggest you do, for example, because you're not going to be able to show me what you're doing. That's actually one of the unfortunate things. Or I might maybe do something about it. Maybe I will maybe next time I will set the setting so that you can be able to share your screens, because right now you're not able, everybody enters, you're a participant, you're not able to share your screen with me and show me what you would like to do. So attend this. Oh, hold on. Make presenter. Okay, I can do that. Okay, can you share? You know how to share the screen? So this is another question. You might lose time trying to do that. Okay, so well, let me suggest something. What I suggest that you do is you send me an email and you screenshot whatever you like to talk about, and then we'll talk about it. Okay, so it's better this way, I think. Yeah, and don't click on this too many times. If you want to talk, just raise your hand and keep talking until you don't want to talk anymore, then lower your hand. You want to talk again? Yes, no? Yeah, go ahead. Just don't put every time lower, open. Just don't use it. Keep it on unless you don't want to talk. Okay, go ahead.
Could I tell you the question?
No, just send me an email about it. I can maybe, if during the time that people are going to do these 10 minutes I said, or maybe less now, I will have a look at it. Okay, that's better this way. Because next time I'm going to find a way how to, if you know how to share your screen using Blackboard, that would be great. But I don't know how you're going to see this. Maybe you're able to see the share screen and then share your screen like this. You can click on that. But I'm not sure that everybody is able to do that, and maybe there's some specificities that need to be, paid attention to. So you don't show to everybody something you don't want everybody to see. So just to avoid these type of problems, right? It's better that you just send this by email. If you have any issues about some question, send it by email. That would be actually more, because you can show me the screenshot of the question. I would be able to see it much clearly that way. All right. And then maybe before the end of the class, just write here that I sent email in the chat. I sent an email. Can you please check? And I can maybe take 2 minutes to have a look at them so we can answer those questions before we close the session, inshallah. That would be maybe a good way how to be able to avoid wasting time and having some issues. Okay, so now I'm going to just close this, and then let's see if you have any questions that you want me to show me. I'm just going to, if you have any questions, you're free to go to ask right now. And from some specific question that I need to check, you want me to see some of the question that you have, just take a screenshot from your screen and then show that to me. Assalamu alaikum again. Let's get back to what we were doing. Actually, Ryan, I just got your email as well as from somebody else. I just received another email from Arwa. But Ryan, you just show me a picture with an image, and then you asking what do you want? So what is it about? Because
I didn't get the idea from these questions.
You didn't get the idea of the question? You did not understand the question, you mean?
Especially the negation of the if statement, or B, if B then Q.
Okay, see, I prefer if you share a question. Do you see my screen, right? Do something like this. You see my screen? You've seen my screen, right? Everybody should be seeing my screen.
Yes, I see.
Okay, so this is what I'm expecting. See, for example, you have this. You selected an answer. That's not the correct one. And then the question is, can you please explain this question? See, for example, like this, it's kind of clear. Okay, I would just like to explain that. And then maybe just do the same with your question. Exactly. This way I understand exactly what you want me to do, right? So try to do something like this. So now, let me answer this question about the truth table of P and not P. Okay, what is the truth table about that? How the truth values have now P and not P. With and, you remember, it has to be exactly both of them should be true, so that the answer is to be true. So if P and not P, that means something and its opposite at the same time can be true. Obviously they cannot be true. So the right answer to this is they are going to always be false. But I'm going to prove that by just doing this very, very clearly, very easily. Let me just select this brush, and then let's go and, okay. Let's say I'm just going to make a truth table about, this is P, and I'm going to put not P, and then after that I will do this P and not P. So since I have only one variable, so I'm having only two lines, right? So it can be either true or false. If P is true, not P is going to be false. And if it's false, not P is going to be true. Now with the end, it's going to be true only if both of them are true. This is true, this is false. With the end, it's false. This is false, this is true. With the end, it's false. So that's how this is going to be the right answer. Okay, you sent something again, and then what's, okay, I'm just seeing again this email that says this picture that is not clear. Let me open that again. And all right, so what is this? A proposition is defined as, well, the right answer is a declarative sentence that is either true or false. That's a proposition. If it's a question or command, that's not a proposition. If it's a mathematical formula, it can be. Maybe it might be a question, might not be a question. Okay, how can I know? Well, it depends on the type of mathematical formula. For example, let me just go back to here. If I put this formula, x plus 3 equal 5, that's not a proposition. But if I put x plus 3 equal 5, knowing that x is equal to, that's a proposition. It can be either true or false, or can be even without true. I can put either 0. That's a proposition because it can be either true or either false. Or even it can be a formula that is going to be 2 plus 2 equal 4. Is this a proposition? Yes. Because it's a formula, but is it going to always be a proposition? No, because it depends. It depends on that type of mathematical formula. A sentence with a variable, well, a sentence with a variable, no, it's not going to be a proposition because it cannot be true or false. If something is variable, it's going to be true or false. So is that what you mean? I'm guessing, because again, he sent just a picture of some question, and then that's the negation of this. The negation of this, for example, what you need to do is to, I think we spoke about this. What we could do is do this here. Actually, this P and Q, the truth table of this P, if P then Q. So, and then after that, what you could do, this is going to be actually much more complicated, but some of them actually are kind of clear. What I would like to, I forgot to mention, the first time I saw it, I wanted to mention that. I forgot to mention that you see the things in a wrong way. See, this is going to be creating problems for you, because you see now, you don't know which one is going to be the one we start with. Now, before, in the previous version of Blackboard, I was able to do something in the, I think in the course, I was able to, in the customization, I think there's some teaching style or something. There's some place where I was able to force a language. Yeah, I think maybe it was here. I was able to force a language, so actually you use a specific language. Maybe let me go for properties. Now I understood that I can't do that anymore. Now, because now your setting is that it shows up as, maybe language pack. Okay, I can force that to be English. How about that? Unforce. Okay, let's see if this is still work. They said this doesn't work, but if it does, that's better. Now, if you reload your page, if it was in Arabic, now you should see it actually in English, and it's going to be from left to right. Now, I advise you to do that instead of having it from right to left, because it's going to confuse you in some formulas. It might not be properly found out. So, but my question here, the question is which one is which? Well, draw the, actually, if you remember, the truth table of this is that it's going to be always true except for one case, and one case only, which is going to be with the first one is true, the other one is false. So let me just maybe quickly do that. If it's true, 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 false, false, true, and false, false. So in this case, they are going to always be, this is going to always be true, unless if it's this one is, the first P is true and the other one is false. And as we maybe spoke, and maybe others might also benefit from that. The only time when this is going to be false, if look at this as a contract or some kind of like a some agreement that we have. If you give me P, then I'll give you Q. So you might give me P and I give you Q, that's true, but the only time this is not going to work is that if you give me P and I'm not giving you Q, because we had an agreement that if you give me something, I give you something else. So if you give me if you review properly, you get a good grade, and then maybe you review properly and didn't get a good grade, that means we did not, this was not respected. Every time else, you might have got a good grade even before, maybe because you did not even review. And if you did not even review and you did not get a good grade, well, this is still okay, because the contract was that if you get a good review, if you do a good review, you get some good grades. So this is still also possible. So anyways, this is something from last week. So this being said, what I'm going to do right now is to move on to this next topic, the topic for today, inshallah. Yes, Ryan.
So, Doctor, what's the correct answer for this question? Because we have if statement or if then, and the choice or the answers is or and.
Well, see, I cannot see this clearly. I cannot answer it because I don't know which one is which. Because I might say that this can be disqualified right away because this is not. But maybe this is the correct one: minus P and Q, minus P and minus Q and P. So if you switch that and send it to me, maybe after we can talk about it. But right now I'm just kind of confused at this question. It's not showing properly to me, and I would like to see the proper answer before the proper options so I can select that. But the idea is I would like to see now, compare with the others, and which one is going to be having the same truth table. So I can, if it's P and not Q, then I have to first have this not Q, is it? And what is the not Q? If I say not Q, and let me just do something not Q, and it's going to be F T. So what is going to be the here that is going to give me that the same truth table is that maybe if with the end I have to have both of them to be true, right? So it can be true. So as you can see, the only time it's going to be false if this one is false and the other one is true. If one of them is false, the result with the end is going to be false. So P not Q, for example, I don't know what are the other options, but if I say P and not Q, this is going to be false. This is going to be true, and this is going to be, I'm just comparing this one with this one. So this one, true and false, it gives me false. True and true gives me true. False and false give me false. And false and true give me false. So actually, maybe the negation of the not this is going to be the correct answer. The not this is actually P or sorry, not P or Q. This is going to give me the opposite of this is going to be exactly giving me this one. Because if I make the negation of this is going to be exactly what it gives me. See this here, this true, this is going to false. It's actually the opposite of that. So if I was able to negate this, give you the negation of what I did, then the negation is going to make it the exact same way like this. And the negation of that means it's not P or Q, because this is going to be, we're going to talk more about these things actually in the next class, in this topic of this class. So yeah, I hope now that for everybody, if you go and refresh the page, it's going to show up in English, and it will force you to have an English. Actually, that's something that I thought was removed, but it seems like I still am able to do that. Hopefully, if it works, that will be better. All right. This being said, let's go and talk about the 1.3. So here in this one, what is that? Is 1.3, not 0.2. actually, yeah. So this 1.3, before going into that, I just would like to, we just spoke about here the propositional logic, and the propositional logic, this is what we started talking, what we did last time, and then now we skip this application, but we skip it because I just still would like you to give you some idea about what that is. So how do we use this propositional logic? It's used to translate English sentences, to do some translation, to keep the same logic behind it. We also use to specify some system specification with the correct, consistent way how to represent things with or and, etc. Doing some Boolean searches with this and that, or this or that, or not, etc. And also to have this some kind of logic puzzles, to have something equivalent. This is equivalent to something else, and this can be a nice thing to have a look at. But anyways, the other thing is actually one of the reasons is logic circuits. Now, if you have, or maybe not, you will be taking the course Digital Logic Design. If you took it, that's what I'm referring to. These actually, every not, an or, an and, these are some actually components that can be put into a motherboard. Now, these things can be used, actually this logic can be used to sometimes simplify some circuits, or to get them into a more economical way, or more efficient way, things like that. So all these are some kind of just some sort of applications of those propositions. But what I'm going to be moving today is we're going to be talking about these propositional equivalences, something that is equivalent to something else. Now there's some kind of logical equivalences that we're going to be talking about, so let's dive into that. An important step used in mathematical arguments is the replacement of a statement with another statement with the same truth value. That's something that actually we do in math. If you do, this is equivalent. If you'd like to prove something, you say that this is equal to that. Let's, for example, hold on. Let me go back to here. If I say, how can you prove that, for example, x? Oh, where is it? So x plus 2 equal, or maybe not even x, let's make it even easier. If I make like 2, again, 2 plus 3 equal 5, or if I make like this is equivalent to 2 plus 1, which is equal 5. So we just replace this 3 with this 2.5. These are exactly the same thing, but just we represent it with something different. We're going to do something similar now with these, with the propositional logic. And we're just going to do that with the compound propositions that are used actually more commonly. And this is actually what we're going to be talking about. So, and there's some kind of rules that we're going to be starting with, just some situation like some terminology like this tautology and contradictions. So a compound proposition, that's maybe a question that I should have had, so I can answer it, because I had it only some people came to my office and talked to me about it. What does it mean? Compounding a compound proposition. Well, this is a compound proposition. It has multiple parts, and you can have actually, so it has negation and it has or. So these are different parts that we can have within the same proposition. That's proposition can have different components in it. So now this compound proposition that is always true, no matter what the truth values of the proposition variables are, is called tautology. And this is an example of a tautology, this one over here. If we do this or, if you have P or not P, so this is going to be P with the or, it's going to be true if only one of them is true. Now, if I have P, these are the truth variable, the truth values, the possible values of this P, so either true or false, and not P then becomes false, true. And if I do the or, that means if one of them is true, the result is going to be true. So one of them is true, result is going to be true. And this is actually the tautology. This is the tautology. Oh, hold on, I have it here. This thing is this one. And the contradiction is actually the opposite. The contradiction, if instead of all true, it's all false. So this is what it means. So we have tautology means they're always to be true, contradiction is always to be false, and then if something is not a tautology nor I'm just finding my cursor, if it's not a tautology and nor a contradiction, it's not none of them, it's called a contingency. That means it can be true or false, but it's not all true. Like a tautology, it's not all false. And tautologies are these kind of examples. So there's maybe some others, but anyways, that's just one thing. Another thing is we need to talk about these equivalences, logical equivalences, and this symbol is this. This is the one that I said I spoke about it briefly last week. So we said that something is logically equivalent. So the notation denotes that P and Q are logically equivalent. That means this is logically the same as this, and we can prove it by also doing the truth tables of both of them. If we have the truth table of P and then we have the truth table of Q, and then we find that they have the same values for every single one of them, that means they are equivalent. That's what it means. So the compound propositions P and Q are logically equivalent if P, if and only if Q is a tautology. And remember, P and only if remember, okay, I need you maybe to help me with that so I can see if we can remember. Remember this? What is the? I don't know. Every time it just leaves. P if and only if Q, and this actually is, if I'd like to draw the truth table of P and Q. So if this is true, 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 false, false, true, false, false. Can you tell me, someone, just what is going to be the truth table of this? Without looking at somewhere to remember. True and true is going to be. Let me go back so I can see what you're saying. True, true, false, false, true. That's correct. I mean, someone gave me the whole thing. That's right. So this is going to be true. This is going to be false. This is going to be false, and this is going to be true. So it's going to be false if one of them, if they're different, if they're the same, they're going to be true. And actually, this, it's equivalent to something else. I mean, if we say that if these two are tautology, this is the question it says. If the P and Q are logically equivalent if P and Q is a tautology. Now, how can this be a tautology? Sorry, if it's a P if and only if Q is a tautology. Now, how can this be a tautology? It's true only if they are the same. So the only way that I can have this to be a tautology, I don't know what, all right, so. Okay, just using some shortcuts without knowing. So the only time is that if they are the same. So P and Q should have the same values. If they have the same values, then it's going to be a tautology. So if they don't have the same values, that means it's not a tautology. That means it's going to be true. So this is what this thing means. Every time I just click on the wrong. So anyways, the point here is the following. This means equivalent. So what can we do with the equivalences? Well, let's have a look. We can show, for example, that this and this are equivalent. So how can we do that? Well, let's start with P and Q. Then we're going to do the P or Q, and then we do the negation of that. So P, Q, that means true, 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 false, false, true, false, false. And then with the end, they're going to be true whenever, sorry, this is not the end. This is an OR. With the OR, they're going to be true if one of them is true. So true, 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 and the other one is false. The negation of that means false, 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 and then true. I just realized that I was writing it actually the negation like this, while they are represented this way. I think I've seen it that actually some are representing it this way. Am I wrong? I think so. That's a different way how to represent it. Anyways, that's why I got confused from that picture actually. Yeah. Anyways, so let's say that this is the negation. It's going to be, I'm going to use the same notation than the books to avoid confusion here. So this is the negation, and so the negation is going to be everything is true is become false, everything that is false is going to become true. So this is the one about, this is the first part. So we're looking at this one, and we got the truth table of that one. Now let's do now the truth table of this one. So we need to do the not P, and then we do the not Q, and then with the end. So not P means every time P is going to be true, it will be false. So here for false, true, true. Not Q, it's going to be false, true, false, true. So this is false, true, false, true. Now with the end, if both of them are false, it's going to be false. If one of them is false, it's going to be false. And only when both of them are true, they're going to be true. And if we look at these two now, we will see that they have the same truth table, which means we can say that these two are equivalent, logically equivalent. So this is what it means. And this is actually going to give us an opportunity if we'd like to prove something, and this is how we can prove it. And same thing here. Now show that this if P then Q and not P or Q, and this is the thing that actually I showed you earlier. And this is going to be they are logically equivalent, and actually this is known as the conditional disjunction equivalence. The conditional disjunction equivalence. Disjunction because they have the or. Anyways, so let's have a look. P and Q. Then we have not P, because we'd like to. I mean, we could have put this here and instead. I mean, or maybe put it, have this calculated immediately after we have that. So this forces me to talk about something actually interesting. Is this, when we present it this way, is it like the only way we can do that? No. So if someone, like for example you, if I was to do this, I would have started by doing P, if P then Q, this thing, this column, I would have put it immediately here, and then I'm going to do this not P and this with that later. But they seem to do it differently, so let's go as if they're starting from here. They're trying to do this one first. So the idea is that they do the steps that are allowing them to reach whatever compound proposition that we'd like to evaluate. So let's now evaluate this one first, and then we'll evaluate the other one first. So now not P is going to make false, false, true, true. This is what we get here. And then not P or Q, so not P or Q. So every time one of them is true, it's going to be true. True, that's false, that's true, and that's true because one of them is true. So this is the truth table of this thing, which is going to be equivalent as the truth table of if P then Q, because it's going to be false only if this one is true and the other one is false. So it's logically equivalent, and that's how we prove that. So as you can see, we can have more examples like this, and this is actually what they're doing is, this is called the distributive law. I mean, there are some kind of, these are laws that something similar to mathematical laws that we might have seen most likely in the calculus or the math courses. So if you have, I'm just going to go to maybe the ones that the associative one, for example, this one. Now if you have P or Q or R, that means it's the same as P or Q or R. So if this is like this associative law, and this is the equivalency that says this is equivalent to that. And same thing with P and Q and R is equivalent to P and Q and R. And we have also the distributive law, which is, notice here we have this or, and here the and. So we're going to distribute this by making P or Q and, so this is P or Q, and P or R, this one here. So it's just we distribute P over the others. Again, this is the equivalency. De Morgan law is the one that we're talking about. If we negate the and, it becomes an or with the negation of each one, single one of them. So the negation of each one of them is going to be then, and then the negation of the or, the and is the or, and the negation of the or is the and. So these are called de Morgan's law. And you have also a lot of different ones, like the identity law. Something and true gives you the something. Something or false, we're going to always give you that something. And this is the identity that stays the same, or the domination, something that is going to dominate over the others. Because with the or, if one of them is true, it doesn't matter what you have here, it's going to be true. So that's why I say domination law, because the truth, the value that we use here dominates whatever proposition we have there. So the same thing with the F, with the false with and, anything that comes after that, because we have one false in the end, is going to be the false. So this is the idempotent laws, which is P or P gives you P, and P and P gives you P. So some of them makes kind of sense, and the double negation, for example, if the not negation of the negation is basically the same thing. Same thing like if you have minus 2, so it's 2. So that's something similar. It's not something that complicated. So these are some kind of also logical equivalences that you can have. I mean, on the right side, I'm just trying to this one over here. And these are logical equivalences involving biconditional statements, or this if and only if. So we can prove every single one of them by using the truth table, and it's going to be the way to prove that these are equivalent. Is that okay? So this just gives more explanation about the De Morgan's law. Remember, the De Morgan's law is about this or and the negation of it. This is actually, we use that a lot in programming, especially in the ifs. If you have if something, okay, where is it? If you have if something, what happened here? If you have an if x minus 2 bigger than 2, for example, to be pictured, if x bigger than 2 and y less than 3, do something else, do something else, and for some reasons, for example, sometimes actually if this is true, well, we don't want to do anything. We would just like to, if this is not true, then we do like this. So we put some kind of not this is one way to do it. But another way is that instead of doing the not is, because I'm going to do more operations, I could just immediately say that this is going to be like if x is less than or equal, so this is the negation of the greater than, it's going to be then 2, and the negation of the and will be the or, and y is greater than or equal to 3. So these two are going to be exactly the same, and they do the same. Now instead of doing something, I can just put immediately into the else, something like that. I don't need the else. This is going to be right here, because I said if the opposite of that is what I want it to be. So this is one way how these actually things, we use them a lot in programming, these equivalences. And the Morgan's law is actually very useful in that case. What is that? Constructing new logical equivalences. In logical equivalences, in table 6 and table 6 and table 7 and 8. I mean, these are the tables. This is table 6 and 7 and 8. That means from these we can generate, also make a proof of something. For example, show that using those rules that not P, if P then Q, is actually P and not Q. So how to prove that they're logically equivalent? This is actually we start from here, and then we look at this to do some kind of equivalences. For example, using this conditional disjunction equivalence, the one that we actually saw here. Where is it? Here. So when we say that these and these are actually equivalent, logically equivalent. So this is the conditional disjunction equivalence. So we're going to say that using this, what we'd like to prove, again, let me do it here. So the negation, again, the negation of if P then Q. So one way we said is that to use the truth table and then try to compare. Another way is to actually say, oh, this is equivalent to, if we use this whole thing, the one before, I think maybe it's even in one of these here. It's actually, that's the one. This thing here is actually this logical conditional disjunction. See, if P then Q, not P or Q. See here, if P then Q, not P or Q. So this is one of the rules. So this, if you say that, I'm just going to say that this is not P. I'm using this rule to move this one to, it's going to be not, and then in between parentheses, I'm going to put this not P or Q. Not P or Q. Then I'm just going to do the negation of that using the De Morgan's law, remember? So that's actually the De Morgan's law, which is, where is it again? Here. Sometimes I don't see the cursor where it is. This one over here. So if I have this negation, I'm just going to apply to that. And also inside of that, I'm going to apply also the double negation, because something is going to be negation, is going to do the double negation. So this is the idea. So I'm going to do this Morgan law, and because I'm having this double negation, and this is going to give me this double negation, is going to be like the P. So that's the, oh, sorry. So that's the idea. So this is going to give me, okay, it's not, hold on, again, it's not P. This becomes and not Q. And this is the double, with the double negation, this is going to be P and not Q. And this is going to be what we wanted to prove. I think so. Okay, I'm not able to with this one. P and not Q, and that's P and not Q. These are then, we proved that they are logically equivalent using those rules, those laws, logical equivalences that we have here. And yeah, that's another way to prove the equivalences. So we now have two ways. The first one was the truth tables. The second one now is about these logical equivalences, using these logical equivalences and with the different equivalences that we have in the laws, etc. Question. Let's go ahead, Ryan.
Doctor, can you repeat this point about the equivalent of if and then?
The whole process, you mean, or one of them?
No, the last one. The last one.
This one here. How I moved from this one to this one, right?
Yes.
Oh, okay, good. So notice that here nothing changes, correct? Also here nothing changes. So what changes is this here. Is that one. And basically what we're saying is that the negation of P is going to be equivalent to what? To P. So,
Doctor,
yeah.
one who have FB then Q. You show it before.
Sorry, stop again. You said one that has F what?
FP.
F for false, right?
Yes.
So I don't understand what you're saying.
You show it before, teacher, on another slide. When you write, not the slide, lecture slide.
Here?
Yes, this one.
Okay. What about this one?
Can you repeat? Can you explain it again?
From here to here? This is, look, this here is exactly the same as this. Notice here. This line over here. So it's not, and then between parentheses, it's not here. Let's see, it's not here. And then between parentheses, what do I have? Not P or Q. Not P or Q. So maybe the question is, where did I get that from? Is that your question?
My question is how not if P then Q equal to not P or Q.
This one here. From this
Yes,
step to this
the
one.
full one.
The
Full one,
first
yes.
the first one. How did I move from the first one to the second one? Correct?
Yes, yes.
Okay. So here, uh, if we have A or B, the negation of that is going to give me what? Can you answer?
Not A
Good.
and not B.
Good job. What about if it was not of A and B? The equivalency is going to be?
Not A or not B.
Good job. Okay. Now, if I change this to be not A, what am I going to have? So not A.
A or not B.
Exactly. But what you did not A, which is A,
Right.
right? So I did this in two steps. So I'm just going to write this here instead of writing immediately not A. I'm just going to do it in two steps. So the first step is that I'm going to do this not P, that's the one, and not Q. So this is the and is not Q, is okay. The or becomes an and, it's okay. The only problem now that we have is this one, correct?
Correct.
So now what you did directly is that you applied immediately that not P is going to be P. I just did it in two steps. I did the first step and then the second step. I'm just going to remove these. What I did is I did this first step when I just distributed the not on everybody. So I had this first part. This is the first not. I changed the or to the and then I distributed the not, the negation, onto the second part. Then for each one of the parts, I have only this one. This one has nothing to do. It's done. But for this one, I need to. What is the double negation? Because I have a rule about it here somewhere. So the double negation is this one. If I'm able, okay. So it's this one over here. So this is where it says me if I have something like this, actually it's equivalent to just have the P, which is actually this is what you said. And this is actually what is written here. This thing is distributing the not, and then this one is the not P. The and is converted because of the negation of the or becomes and, the negation of the Q becomes not Q, and then this is what it gives us. And then the double negation gives us that this actually is equivalent to P, and then the result are the same because I'm not touching the rest. And this is actually telling me that this is equivalent to this, which is what we wanted to prove.
Yes, doctor. My question, how did you convert this one for not B, not if B then Q? How did you convert it to B and not Q?
This here. Well,
No, on the left. On the left one.
this, well, I'm still I don't get it. Okay, let me tell me again. Your question is about what?
This one on the left.
This one here.
Yes, yes.
Oh,
How did you convert it?
how did I convert it to this? Right?
Yes,
Okay.
yes,
Now
yes.
let's remove the nut. If we remove the nut, let me just do something. I'll just do the highlight. If I remove the nut, what do I have? I have only this thing. Correct? I want to focus on
Correct.
this. I've seen just earlier, and I did the proof using the truth table, if you remember. I proved this, that this here is equivalent to this. That's what I used. So here, I'm going to replace this P, if P then Q, with not P or Q. Let me go back. Or maybe that one. Okay. So I'm going to not P or Q, which is from here as well. This is actually summarized also here. This is what we proved. All this not P or Q, remember? Not P or Q. This is what we proved, not P or Q.
Right.
So that's where I get that from. And this is how I started. And then I added the negation. And from the negation, it just went through. So this is, says I'm using the conditional disjunction equivalence. This is the example 3 that we're talking about. And then after that, I used this, the Morgan's law. They put them second because the first one was about not and or something, I'm guessing. And then the double negation law is the one that does this, remove them and simplifies that. Is that okay now? I think, yeah, we had some differences to understanding. Now we're clear, inshallah. And based from this, you can just construct different kind of equivalences. And this is, again, another way how to prove these. How can you prove that this whole thing is equivalent to this? So this is a good example of, see, if I have, because of this simplification, this something, I maybe have a complicated, if I had to build a circuit with this thing, it's actually making more sense to use less components than if I use it like this, rather than if I use the long representation. So again, how I can do that? I can prove that using the truth tables and then follow the truth tables, etc. Another way is to use the different equivalences or laws. So here they said what they're going to do is that they're going to take this and use the second De Morgan's law just to apply it to all of these. So that means this here, I'm going to take the negation of P, so this is what I get. The OR becomes an AND, and then I'm going to put the negation of whatever is between parentheses. Right, so all I did is just I negated this OR to become an AND, and the rest, this is P became not P, and this whole thing, I'm going to call it whatever it is, R for example, becomes not R, because I just put R. This is the same, I just put it there. Now what I'm going to do, again, do the same thing with this one over here, with this one over here. So I'm just going to do the same thing. So I'm not touching this part, you see it's the same, but I'm going to do this, distribute the negation. So the negation over the not P, the AND negated will become OR, and the not Q. So that's the second, again, the Morgan's law. And then here I'm just going to apply the double negation. Double negation, this here will make it just P. I don't touch the others. So every time I just change one small thing. And then here, what I'm going to do, I'm going to do this distribution. I'm going to distribute this, not P and P. So this gives me not P and P. This is the first part. Then I'm going to distribute not P or, so this is going to be the or, sorry, and not P and not Q. So I distribute this and is going to be, hold on, I made a mistake. I'm distributing this, I'm just confusing you. I'm distributing this and over this first one and over this second one. So I'm just going to take not P and P. So this is the one, I'll take this one from here and I'll do the distribution to get this first part. And then it's going to be the OR, not Q, is going to be with the and this one, the and I'm going to distribute it to the other one. So not P and not Q. So the and is distributed, as you can see. This is the and is going to be in two places. I'm going to distribute into the two places. And this is the second distribution law. If you go, okay, what is the distribution law? Let's go back here, and you can see the distribution law is this one. So it just says that if you have this OR, it's going to distribute the OR with the end plus with the end of this one or that one, and this one or that other one, that's PR. And same thing here with the, if it was the and then the or, and just going to be distributing the and to each one of them. So the and, see, is going to be the one that is going to be distributed. Sorry. The and is going to be the one that I'm distributing here. And the or is going to be this or over here. It's going to be all these two parts. So basically I'm distributing this and in the two places. And is going to be with this one and the end is going to be with the other one. And or is going to be in the middle. So there was a question, I think. Yes, somebody raised his hand. No. Yeah, go ahead.
Doctor, can you explain it more at this point?
Right, let's try not
How-
to touch your microphone because you just touching. Okay.
I don't know.
Yeah, it's okay. Which point? This is a rule. This is a law. If you would like me to prove it, this is what you want to prove that. This is how.
Yes, how did they confirm from
again,
three?
truth tables. You can confirm that from truth table. Let me just maybe give you another example. Now, if I have 2 multiplied by 3 minus 5, what are you going to do? It's 2 multiplied by 3 minus 2 multiplied by 5. Right? Am I right?
Again, teacher.
This here. Does it make sense or not? You've seen this before?
It's right. Yes.
So the same thing.
Uh,
Replace the x with
or.
and this one with or the opposite. So no matter what you have here, you have P and Q or R. This is equivalent to having this P and Q. I'm just checking this one first. I can just go back. So P and maybe hold on. Let me go to here. This is where I can have a better. P and Q or R. This is going to be, I'm going to distribute this P and to each one of the others. So this is going to be P and Q and P and R. So these are the two. I'm distributing the and with the P to the others, and then what is remaining is this R here. And if it was actually something else, if this one was the opposite, it's going to be the opposite. These are these are the distribution laws. If it was or, sorry, and I'm just going to distribute now. This is going to be the and this is going to be the or. So if you want to prove that, well, you can try to the truth tables, and this is going to be able, you'll be able to actually see that it's actually the same values. But the idea, these are the rules, and we are going to assume that they are correct. If you are not sure for one of them, no problems. You can double check. Just use the truth tables by yourself. Look P, Q, and then see if this is going to be the same truth tables. If it give you the same truth values. If it's the same, that means okay, it makes sense. So that's the same thing, because we cannot always prove everything. We prove them once and then we use them. So this is actually the idea. You just have to use this. So what we did here is that we distributed the not. So the not here we distributed. So then by using this not P, the or becomes an and then not the whole thing, this whole thing. I just negate that. Then I again applied the Morgan's law to negate what's here. So this becomes not P. The not of the and became an or, and then not Q. Then we here we just do this double negation just to clear this here, and this is actually the only change that we did from here to this one. The only change is that this one became P, because not P is P. We've seen that with this double negation. And then what we are going to do again is distribute. So not P and, I'm going to distribute not P and P, or not P and not Q. So here, not P and P. This is actually something that is going to be not P and P is never going to be true. With the and, never going to be true. Actually, again, how do I have that? You can prove that same thing, or you can use whatever this domination laws that we have. Sorry, not one. Which one? This this one here, this negation law. I'm just trying to use this here. So that negation law is you have something and its opposite, or something or its opposite. So it gives you that thing. So this is the domination law. So this here becomes false. False or anything, the false is not going to have any effect, right? If I have false or something, it doesn't matter. I don't know why they just did this commutative law for disjunction. They just oh, what they did, they distributed. No, what they did here. Okay, so up to here, understanding what is happening, because not P and P, it's not possible. It's only going to degree F. Now, what they're trying to do. To me, I would just take this out, and that's it. That's what I mean. This step that they're using is not really necessary, because something or something that is always false, or something else. What is going to distinct to say which one is going to be true or false is actually the other thing, because this with the or, if one of them is true, the other is going to be true. If one of them is false, well, it doesn't make. We need to check the other to know if it's going to be false. As you can see here, you see this is exactly the same thing. So I don't know what they did here for. By the commutative laws for disjunction, I think this is absolutely not necessary, because all we have to do is say that if we have this, if you just swap them, doesn't make any difference. They just move them around. So you see what they did? They took this, put it in the beginning, and they swapped the positions around the or. It doesn't make any difference. I don't know why they did that. So this is actually absolutely not necessary. And all you have to do is to move from here to here. Actually, they have maybe this identity law. Something or F is going to always give you something, or this one. Something or F or false is going to give you that same thing. That's the identity law. So if you give me with the or something that is false, this false is not going to change anything, because I have to check this one. This is the one that is going to decide if it's going to be true or false. And that's actually what they're using here to say that actually because of that, because of the or, this is going to be just removed. All we are left off with is actually this not P and not Q. And this is going to prove that this whole thing can be simplified at not P and not Q. And if you had to decide to draw some kind of diagram of or some logical circuit with this, the components are going to use 1, 2, 3, 4. Here you're going to be 1, 2, 3. So you saved one component, and this is actually give you the exact same result. So as you can see, we can also do a lot of exercises based on that. The main idea is that we're going just to always use this same logic, that using one rule to move from one step to another. Remember, okay, maybe I was about to skip this one, but I think it's an interesting one. See here, how can we move? Again, this is the same example that if you have if P then Q, but here our P is actually something more complex. Let's call it this is A and this is B. If A then B, this is going to be giving me not A or B, which is basically, this is actually, I'm just using AB because it makes more sense. Let's show you this here. Now let's replace this A, B, so it can be actually more clear to you. Not A or B. Except now the A and B's are actually more complex, as you can see. Sorry, I forgot. This is not, because this is the A, this is not A or B. And the same example, they said it here actually. It's example 3 again. And then from here again, you're going to just do these, apply the negation of this is going to be what the Morgan's law based on here. So it's going to be not P the and becomes or, not q, and this stays the same. Don't touch that. And now that we have these, we're going to do some kind of associative and commutative laws by for the disjunction. This is actually a mouthful of things that have been done. So basically, what they do is take this and okay, hold on. See what we have here. It is or, and this is or, and this is or. That's the same operator, correct? It's or. It's like we have 2 plus 5 plus 3 plus 2. So 3 pluses, 3 ors. Now this thing, you have parentheses, something like this. So what they're doing is that they're moving things around. If I do is this, I'm going to do is 2 plus 3. Can I do that? Plus 5 plus 2. Obviously, because they are the same operator, I can just move them around. So this is what they did actually. They moved around the same operator. Actually, the best way to do that is they did this, remove the parentheses. If we take that, sorry, up. If we take this, and then we remove the parentheses because we don't need them, they're all the same level. So if I have not P, or not Q, or P, or Q. So now I'm going to move these around. I'm just going to put this P next to this not P. So that's why we have here, I'm going to put P next to not P. So we have not P or P, and then I'm going to put this not Q next to this Q, and I have not Q or Q. So not P or P with the or, it's a tautology. It's going to be always true. With the and, it's going to be always false. Same thing that we've seen just earlier. So with the or, not P or P, this is going to give me true. And then not Q or Q is going to give me another true. So this here, this whole thing is actually true, always true. So this is proving that this is a tautology. I think it's kind of mind binding a little bit, but it allows to understand. Yes, Ryan. By the way, it's not only Ryan that has the right to ask questions. Everybody can ask questions. Go ahead.
Doctor, you said before if or I mean false does not affect. So now true T, does it affect or not?
Hold on, stop. Let's just first let me understand what you're talking about. I said false does not affect. False
in the
or
previous example,
something.
Yes.
Yes.
In the previous example, you said that.
This is equivalent
so now,
to this. Correct?
The same or not?
Hold on, you're touching the microphone. I'm not understanding what you're saying. So you said this is. We spoke about this correctly. Yes. Okay.
Yes.
Then
does T affect or not?
Does what?
Does T have the same thing or not?
Yeah, T or P. No, this is going to always be true. With the or, it will be the same effect if I have 3 and P. Now, is it always true? Well, no. Maybe if the P is false, P can be true or false. Now, let's have the different possibilities. Here, P can be true. It can be false. With the and, true and true gives me true. True and false give me false. So I cannot just tell you that actually this is going to be true, but I'm going to say this is going to be P. So if you tell me
it depends on the proposition.
Yes. So now if you tell me now this here, what we're talking about is that we have something and its opposite, or its opposite. Something or its opposite. So if something, P, is going to be true or false, not P is going to be, sorry, I said true or false, not P is going to be false, true. Now if I put the or in between, something true or false is going to be true. Something false or true is going to be true. So it's going to always be true. So this here is going to always give you this thing. And that's the rule over here. This one. With the or, this negation law, see. With the or, something, I don't want to hide. So P or not P is going to give you true all the time. And then P and not P is going to always be false. So depending on the or the and, the result is going to be different. This kind of question, but it's in truth. Yes, you could. But if I'm asking you to also use the equivalences, then you should use the equivalences. You should learn how to do both. But you can always do one or the other. For example, you can do something, then check it with the truth table as well. Truth table is actually sometimes easier because there are less rules to remember. There's only negation, or, and, etc. But when they become like more complex, like P, Q, R, S, T, all the best trying to do these truth tables, because you remember with the truth tables, the number of rows are going to be 2 to the power of how many variables do I have? So 2 to the power of 4 is going to be 2 times 2 times 2 times 2, which is 4 times 4, which is 16. Now imagine I just give you 5 variables, all the best. So it's going to be 32 now. 32 rows is going to become very complicated. Sometimes it will be very hard to do that. It's going to be much complex, and it's prone to mistakes now, because true, false, true to F, and then you can see now, even when I do the writing, I might, by mistake, not write them on the same line, and then they become like a trouble to follow. That's why when actually we have many variables, it's the best way to go, with the easiest way to go is to go with these equivalences. So these are all different type of things, or different type of examples. Okay, other questions? Okay. All right, so let's stay here. What about these? A compound proposition is satisfiable if there is an assignment of truth value to its variable that makes it true. That is, when it is a tautology or a contingency. Okay, that's the terminology. Okay, so a compound proposition is called to be, it's said to be satisfiable if it's either a tautology, it's always true, or it's sometimes true, sometimes false. But it's not going to be satisfiable if it's always false, because then it's unsatisfiable. So if you say something that's a compound proposition is unsatisfiable, that means it's always going to give you false. Sorry, false. So it's always going to be. And what's the name of the opposite of tautology? Remember? It starts with C. Somebody?
Contradiction.
Thank you. Contradiction. So we have contradiction, that gives you always false. Tautology gives you always true. And contingency is sometimes true, sometimes false. So then again, if we say, okay, prove that this is satisfiable, we're just telling you that this actually is not a contradiction. That's what we're saying, because it should be either a tautology or something that can be true or false. It's a contingency. But if we say, okay, prove that this is unsatisfiable, well, then you have to prove that it's going to always be false. So for the sake of time, I'm not going to spend more time on that. The application of this satisfiability, there's a lot of different things that actually use this. It is possible to be true, or it's not impossible. Some of the examples is that the n-queens problems. This is something we will talk about in data structures actually, which is actually how to put 8 queens such in a chessboard that has 1, 2, 3, 4, 5, 6, 7, 8 by 8. Actually, that's the idea. So that's why you have 8 by 8, and then you have 8 queens. You have to put them in a specific way so no one threaten anyone else. So if you know about the chessboard, the queens, they can move in horizontal, vertical, horizontal, and then also in diagonals. So if we put some queen here, we don't want to have anything in the diagonals, anything in the same row, anything in the same column. and even in the diagonals, all diagonals. So that's why there's a way how to do that programmatically. There's actually something we use that actually for also talking about recursion. But that's another story. Also Sudoku, if you know what this is, actually there's a way how to solve this. Again, this satisfiability problem can help with that. So I'm not going to spend too much time on that. And let's take a small break because I'd like to prepare the quiz, the real mini quiz for you. And then so you can take that mini quiz right now. Hold on. Let me just prepare it. Yeah, if you have any questions, just ask them now. Yes, Ryan.
Doctor, I sent the picture of the question again by converted to English.
Okay, good. But I think I answered it, right? Is it a different question or the same?
No, it's the same, and you explain it. Okay, but
Okay.
it's different. No.
Okay, it shows different to you. I think that's good now that we said it this way. Inshallah. I think people have finished the test, so let's move on. I would like just to go and talk because now time is running. I would like to be able to finish like in half an hour at least the main things about the section 1.4 about predicates and quantifiers. So I will just skip giving too many examples, but I've just also found that some of these slides are kind of dense. Now and there's some redundancy, some repetition in it. So I will just move to the part that actually I think summarizes all the talk about these predicates and what do they mean. I mean, so right now what we have is that we've been using these proposition, which can be either true or false. And when we have something like this here, well, it's not a proposition. That means because they are of those variables. So now these variables, actually this propositional logic cannot actually express properly the meanings of all the statements in mathematics and natural language. Natural language, every time you see that, that means our language, human languages that they use. So for example, so if we symbolize the argument x runs faster than y runs faster than z, hence x runs faster than z, it's clear that it is not something that if p, both p and q, then r as an event. So the idea is that what we'd like to do is that we'd like to have these propositions that sometimes they have some kind of variables in them. Let me just jump to, for example, this one here. The statement x is greater. People, are you hearing me? Oh, sorry. Oh, I forgot to share the screen. Yes. Sorry. Yep. Done. I forgot to share my screen. Thank you. Just don't be too late. If you see me talking and this doesn't show anything, just immediately stop me. Okay, so now it's showing. All right, so what I was saying is that the idea is that if we have something that says this statement, x is greater than 3. So this statement here is not a proposition. But we can still try to make sense of this by actually taking this x, which is the subject of this whole story, that x is greater than 3, and taking it away. And then keep the rest. So if we take out the first part, this variable x, this subject of the statement, because we're talking about x, right? So x is the subject of this statement that it is greater than 3. Now we take this x apart. We take the subject apart. What we're left off is something we call predicate. This predicate is now, in this case, is greater than 3. So it refers to something that's going to be greater than 3. And then we can represent it this way. With this predicate is actually depending on x. So if we say x is greater than 3, if we represent by this p of x, that means the predicate is greater than 3. And then we can put some values in this x. And then we can say p of 2. P of 2 now becomes a proposition. Because now I'm saying 2 is greater than 3. This obviously is going to be false. That means, but again, a proposition is a sentence that can be true or false. So that's the idea behind this, a different way how to represent those propositions and in a way that is going to give us more flexibility. So now this P of X is going to be representing some predicate that is going to be depending on our subject, which is X. If I specify the X, then it becomes a proposition that I can have a value true or false. If I don't specify the X, it just stays as some kind of a non-proposition. So the statement P of X is also said to be the value of the propositional function P. So P becomes like a function that is depending on X. So at a specific X, then it's going to give us that. And then once a value is assigned to the variable X, then this P of X, this predicate of X, becomes a proposition that has a truth value. So that's what I wanted to say. So let me just actually do this, it will be much better. So these are examples. Let P of X denote the statement X greater than 3, which is this what we said. What are the truth values of P of 4 and P of 2? So now we can put 2 is greater than 3. I'm going to say this is false. P of 4 is going to be 4 greater than 3. This is going to be true. So this is how this works, and these are all different examples that says okay, the same thing. If I say let's A of X, again you see this, it can be anything. We don't have to always use P for predicate, but you can use A of X. Denotes the statement computer X is under attack by an intruder. Now suppose that the computers on campus only, we have CS2 and MAT1, are currently under attack by intruder. So what are the truth value of A CS1? So A CS1 means computer CS1 is under attack by an intruder. But we said that right now, right now, only these two are currently under attack. So if we say that A CS1, it's asking that CS1 is under attack, but so this is actually becoming false. It's going to be false. Actually, let me use the pen. So this here is going to be false. Okay. Why? Because it tells us that assuming that only these two are under attack right now, that means CS1 is not part of them. This is going to be false. What about ACS2? Well, it's going to be true. Sorry, this is going to be true. And MAT1, well, same thing because it's part of what actually is happening. But this one is going to be false. So the idea is that we represent now those statements that were not propositions and with some variable, and this gives us some kind of flexibility that we can use to also, if we have, for example, some two variables like here, x and y, we can also do that and put those two variables and use them to have this statement that we can assess now. If I have q, if we say like q of x and y denotes this, if I say q1 2, is this true or false? Now all you have to do is replace the x with 1, the y with 2, and then let's ask the question, is this true? Is 1 equal 2 plus 3? Obviously this is not true, so this is going to give us, this is false. How about this one? If we replace x with 3, y with 0, so is 3 equal 0 plus 3? This becomes true. So that's basically it. It's just we are going to use those predicates, which refers to like a sentence without a subject, and that subject we can have like some kind of represented as a function, and that function can then become a proposition that has a value, either true or false. So again, different examples that with the same idea. Now I just would like to jump to these quantifier, and this is actually something that most likely you've seen already, but we're just going to talk about them more. So what are those quantifiers? Now quantifiers are something that gives some kind of range of values, range of elements. Now this kind of ranges in English can be all or some of the numbers, or many of the numbers, or none of the numbers, or some, or few numbers. So these are actually this type of quantifiers that gives us some quantification, some numbering about the different values. Now we have two types of quantifiers that we're going to be focusing on. Universal quantifiers and existential quantifiers. Basically, we're going to focus on two things. One that says for every element, this is the universal quantifier. So every element, All right. Ins, that this is the universal quantifier. And existential, that means there is one, at least one. If there's at least one or more, but if there's at least one, there is something that exists, something that makes this to be possible. And then this is how we're going to represent them. So let's have a look. Let's have a look at the examples here, and then I'm going to read here the thing. Now, where is my, okay. All right, so I'm here. This here means for every x, p of x is going to be true for every x. So that means this is going to be true for every x. So we represent this symbol. This is the universal quantifier. And this one here, this one with the reversed, like with the mirrored e, is the existence, the existential. There is an x making p of x to be true. So that's the difference between them. There is an x that makes p of x to be true. The difference between them is that we're talking there's all values that can be x are going to be making this p of x to be true. Here we are saying there's one, at least there's one. Maybe there may be more, but at least there's one. There is an x that exists that makes this to be true. Now, when we say there's an x, we need to talk about another thing which is very important that goes at this domain. I mean, when we say domain, it might be, it's a big word that just mentioned, okay, what is that x? What's the definition of that x? Is that x like all the whole numbers? All the real numbers, the decimal values? Or is it like all the possible values from a selection, 2, 3, or 4? This is like, these are the values that the x could be. And then when I say for every x in this range, or is it in the whole possible values, this is the domain. This is what we talk about, the domain. So now we say that the universal quantifier of p of x, which is in this case the universal quantification of p of x, this is the representation of it, is the statement that p of x for all values of x in the specific domain. I mean, in this case, we did not represent what domain is. It is all x. So that means everything possible in the world that can be x. Generally, we're going to mention something. What does it mean? But right now, we're introducing this, universal quantifier quantifications and this existential quantifications. So now let's have a look at something that maybe give us more details. Let's have a look at here. And before, as we pointed out, specifying the domain is mandatory actually for when we have these quantifiers. So when we have this right now, we don't say that it's not really representative, but we should have like what is the domain. So let's have a look at an example here that explains the domain on how we use that. Let's p of x be the statement x plus 1 is greater than x. So this is my p of x. This is the predicate. X plus 1 is greater than x. What is the truth value of the quantification? This. So this is going to be true for which x? Where the domain consists of all real numbers. That means now we're talking about all real numbers are going to be put into x. If we do that, is p of x going to be true regardless of what real number? So basically, sometimes most of the time we represent this for every x which is part of the real numbers. Maybe you saw that, maybe you didn't. P of x is to be true. So this is actually the domain. We're specifying that actually this x is part of what? What are the values of x? And these are all real numbers. That means this is all the real numbers that we're representing. And if I take every real number that I can think of, is this rule going to be true? If it's yes, that means this is going to be correct. I mean, it's true. If not, then this is not possible. This thing is going to be false because there is maybe one that makes it not possible. And that's the idea now. We can have like one predicate And because the subject can be so many different things, it can just now be represented as some sort of a function depending on the x. And if I say this universal, it means I'm asking all possible values would make this to be true. And then the other example, well, this is also for that. For the other example gives the false, but I'm looking for the existential so I can see that. But where is these are talk about this, the existential. This is for the existential quantification of P of x. So that means there is an element of x in which, in the specified domain, such that this P of x is going to be true. Which means this is going to be true. So again, this is the same thing. This is going to be true. Okay, where is it? When there is an x where P of x is going to be true. Now, the difference between these two is that if I have the statement with the universal quantifier, this universal means P of x is true for every x. And this one, there is at least one that makes this P of x to be true. So if I have only one, this is going to be true. So this actually exists, is, well, depending on how you see it, is the easiest way to find it to be true, because you need only one that makes it true. But also maybe if you have different possibilities, it's hard to find that one that respects that rule. So another way to represent that is this in the top here, is that when you have for every x that you have P of x is true, that means P of, if you have, take the first x that you can think of, this should be true. And take another P of x, it should also be true. Take another one, it all should be true. Take every single x that you think, it has to be and. You have to take every single x, put it here, take the value and see if this is true or false. If this is true, if one of them is false, now this is the thing with this universal quantifier, because this is like an and. If one of the x's in the list of different x's that I can use does not respect that rule and gives me false, as you know with the and, if one is false, it does not even need to check all the others. If one is false, everything is going to be false. So to be true, so I can have that, it's actually very hard because I have so many different numbers that I need to check to make it true, and they all have to be true, all of them, so can this to be true. But for the existential, it's like an or. I just need one of them to work. Maybe this one doesn't work, maybe this one doesn't work, or maybe this one is the one that is making it true. And because this is an or, one of them true, that means there is an x that makes this P of x to be true. Here we say all x's makes P of x true. Let me check the question. Yes, so yes, go ahead.
Doctor, so if we have two statements are true, will be false or also true?
Two statements? You're talking about which one? The existential or the
Existential.
why is this not okay, so it got I have a bug, I'm not able to write anymore on them. Alright, let me close this. Keep discard. Alright, shift F5. Alright, let's go back to your question. Which one again? Sorry, this one?
Existential. If we have two
okay.
x.
Yeah. For the existential, because it's like an or, this is how you should remember it. If one of them is true, that's enough for the whole thing to be true. Because the existential says there is an x, at least one, that makes P of x to be true. Right? So
if there is more than one, it will be also true.
So sorry?
If there will be more than one true,
yeah,
it will be also true.
Exactly. As opposed to the universal one, where they all have to be true. If only one is false, all of them, like you have 100 x's, all of them are true but one, then the whole thing is going to be false. This whole thing is going to be false. You cannot say that every x makes p of x true. That's what it means. Here what we're saying is that with this universal quantifier, we said every x in a specific domain, or when we decide what else the x's can be, all the real numbers, all the positive numbers, all the negative numbers, that makes p of x true. That means every single one of them makes p of x true. But with the existential, we only need one. There is one in this pile of these numbers, either the negative ones, positive ones, doesn't matter, whatever the domain we specify the x to be from, there's at least one that makes this true. And that's the idea behind this. So for example here, let's p of x denote that x is greater than 3. Now if we ask the question about there is an x that makes p of x to be true, where x now I'll specify the domain. The domain is important because what is x? Because I can tell you x is maybe 0, 1, or 2. These are the possible x's. So if I tell you that, the answer is going to be different rather than if I tell you that the x is actually all real numbers. If I tell you all real numbers is what the x can be, this is the domain. So if I mention that the domain now is all real numbers, it's going to be different than if I tell you the domain is actually only the values 0, 1, and 2. If I tell you 0, 1, and 2, that means I'm going to test. Is p of 0, is it going to be making this true? P of 0 true? No. P of 1 true? No. P of 2 true? No. No. So none of these are going to make p of x true. So if I tell you this, given this domain, this is going to be false. However, because the domain now here says that it's all real numbers, that means take all real numbers, and if you find one of them that makes this to be true, then this is actually going to be true. So if I take one number, 0, that's one of the real numbers, but this is making it false. Okay, I can try another one. -5. Well, still, it does not make p of -5 is not greater than 3. It's false. But what if I say, okay, 70, well, 70 is greater than 3. So, yes, there is an x in all the possible real numbers that makes p of x to be true. So that's basically the idea. And then this is an example of the domain. So let's have a look at this. What is the truth value of there exists an x that makes p of x, where p of x is the statement x squared is greater than 10. And the universe of this course consists of the positive integers not exceeding 4. Okay, now this is kind of big word that says one thing. The domain is going to be positive numbers, and for some reason they excluded the 0, but it doesn't matter because 0 something does not make this to be true. So they say that your domain now for the x are these values that do not exceed 4. That means it's going to be, even if you include 0, let's say 0, 1, 2, 3, 4, because 0 is not negative. Is it positive? Well, maybe it can be both positive and negative. So regardless of this discussion, I'm just going to include it just to avoid having any troubles with it. So now if I say that the numbers that are not exceeding 4, now if you take this, take 4, the biggest one, square it, that's going to be 4 times 4. Correct? Gives us 16. So 16, is it greater? Does it make this to be true? Well, yes. Right? What is this? So it's made it true. That means there is an x. Because I'm looking only for one. There is an x making this p of x to be true. And just testing this one made it. If I had tested with 3, 3 times 3, that gives me 9. So this does not make this to be true. But because only among all these, one of them makes it true, so that means this whole thing becomes true. Now if this was like there is, it all, for all x's, p of x is going to be true, knowing that x's are going to be integers from less than 4. Well, this is not going to be true, because then I need to check all of these to be, this one should be true, this one should be true, should be true, should be true. And actually, this only one is true, the other ones are false. But because of the exist, I'm just looking for one that makes this work. And that's the idea behind these quantifiers. So let's summarize, because I don't want to take more time than what we're supposed to. The quantifiers, there's the existential that says there is one from a domain, from a list of values, that makes the predicate to be true. And this predicate, it's a predicate up until when I put a value in it, then it becomes a proposition. When there is a value, this is p of x, this is a predicate, but then p of 4, this is now a proposition. It can be true or false, that's what I mean. P of x cannot be true or false because it cannot tell you anything, but as soon as you put a value, then it becomes a proposition that can be true or false. So I think, yeah, I don't know if this is again summary of some of the things. Let me see if I'm mistaken something else. Okay, yeah, there is also this precedence of quantifiers, and I'm going to stop here. This part I'm going to talk about it inshallah maybe at the beginning of next class. There's not much actually that is remaining. The only thing is how to negate that. So maybe I can have time to just maybe in these few minutes to talk about it. So the video actually recording will be much easily contained. So the other thing is, now if we talk about the precedence, the quantifiers, this like for every, or the universal, and exist have higher precedence than all the others that we have seen before, which means, what are the others? So if we have this, all, and then exists, these are going to be the first one. Then we have the negation, then there is this and then or, and the if and only if. You remember what we're talking about. So for example, if you have something like this, they said something like this, when we have, there is, for all x's, there is p of x or q of x, is the disjunction of there is all p of x and q of x. In other words, this is going to be this or just that one. It's not actually this. That's what actually that we need to talk about it. So the precedence, that means it is going to, this one is going to apply only to this first one. So if you want it to be like this, well, you have to put parentheses. If you put this like that, the meaning is going to be this one or that one. But if you want for every x, then p of x or q of x, then you have to put the parentheses, because without those parentheses, we're going to fall into just this one is going to be first, then we apply the other one. That's what it means. The last thing is how to negate. That means the negation of every, there's all x's makes p of x. That's what we're talking about, or the existential one. And let me just go to that. And this is the negation. That means if I negate this thing, what does this mean? Now, let's just have a look. I said for every x, p of x is going to be true. If I say the opposite of what I just said, the negation of what I just said, that means there is one that makes not p of x true. So that's the negation of that. And again, if you'd like to prove that, we can actually see if they are logically equivalent. We can maybe do that. Maybe I'm just looking at the time and I find that Well, I'll probably leave that for later. I'm just going to talk back, review that inshallah next class. But the idea is that we can, if you negate an for every, it just gives you this existential. All right. I think I'm just going to stop here. I don't want to rush things, and we'll talk about those later, inshallah. So let's summarize up to what we've seen about this this existential. Maybe this one summarizes it a little bit. When we have this existential, for the universal quantifier, that means for every x in a domain, this p of x is going to be true. And if we do the existential, that means one of the x's in a specific domain will make the p of x to be true. In that regard, to remember them, just remember the or and the and. The existential is with the or. One of them is enough to make everything true. And the universal, that means the and. All of them have to be true, so that it can be true. All right. Any questions? There is no screen share. Well, I just it shows that it's sharing, but did it disappear for you? Maybe some don't have it. Yeah, because I was sharing.
Teacher, there is a screen.
All right. So anyways, I will stop here, inshallah. Next class, we will continue talking about those the negation of the quantified expressions, and we'll talk about them in more detail, inshallah, so we don't rush things up. Even though we are kind of actually a little bit behind, because normally we have other two things to talk about, but we'll try to make this work, inshallah. All right, so thank you very much, and see you next week, inshallah. Yes, Ryan.
Doctor, the next mini test will be by the same structure of the first one.
Yes.
It's 8 minutes and the same number of questions.
Yes.
Okay, thank you, teacher.
Welcome. Okay, assalamu alaikum.